Sometimes to understand a problem, you've got to dig deep. Today, we'll dig deeper into maximum likelihood estimators and learn that they are functions of a sufficient statistic. So they should be kind of like good estimators because they use in some way all the information contained in the data. We'll begin this second lecture on maximum likelihood estimators by stating a theorem, which is kind of something good for maximum likelihood estimators. It just says it's always a function of a sufficient statistic. So before, sufficiency reminded us of a full glass of beer, so that's why I put these here. So hooray, our maximum likelihood estimator is going to be based on a sufficient statistic always. So if we go through this recipe of writing down the likelihood function and then finding the parameter values which maximize it, we will come up with estimates which always will be based on sufficient statistics. The proof of this is actually quite simple, and it goes back to the definition of the likelihood function. So here's the proof. Let's say I've got a parameter theta, and I've got my random sample x1 through xn. So I guess let me give more of a preamble to the proof. Let x1 through xn be a random sample from a distribution with PDF or PMF. This could be either, depending on some parameter theta. Let's just assume there's one single theta. Okay, then the likelihood function, remember, is given by the product of these marginal PDFs at the xi's. Okay, now what we also know is that since x1 through xn are independent and all have the same distribution, this product of the marginal densities is the same thing as writing down their joint probability density function or joint probability mass function. I guess it's evaluated at these random values. So it's just the joint density or probability mass function of x1 through xn. And we have to think back to how we showed that a statistic was sufficient or how we found sufficient statistics. We used a theorem called the factorization theorem. And if we could factor our joint PDF or joint PMF of the random variables in the sample into the product of a function h, which involved just the data, so just the data, and a function g, which is a function of some statistic and theta, then then this statistic, when we found this factorization, that was a way of showing that this was a sufficient statistic for theta. Okay, so basically we can write the likelihood function if we have a sufficient statistic. So let's say if we have a sufficient statistic for theta, that means we can write our likelihood function exactly like this. We can write it as the product of a function g, which depends on the statistic and theta, and of a function h, which depends only on the data. Now, if we think about the maximum likelihood estimator being the value of theta in its parameter space, which maximizes the likelihood function, then it's really the value of theta which maximizes this product of functions and we see here that this part does not involve theta. It doesn't involve theta. So if I'm just maximizing this thing with respect to theta, it makes no difference what the value of this h part is. So I can write this again, that the maximum likelihood estimator is really just the value of theta, which maximizes this function g. And so it means theta hat is determined entirely by the value of the sufficient statistic T1, T of x1 through xn. Okay, so always when we have a sufficient statistic for the parameter theta, if we compute the maximum likelihood estimator of theta, then that estimator will be determined by the value of the sufficient statistic. This means theta hat, the MLE for theta, uses all the info in the data set x1 through xn about the parameter theta, which sounds like a good thing. So we'd like to use the data as effectively as possible. So when we compute our estimator for theta, we don't want to throw away any information about theta which is contained in the sample. So the maximum likelihood estimator does not throw away any information about theta, it uses it all. Okay, that doesn't necessarily ensure things like unbiasedness or the smallest possible variance, but it's a good start. It's good to know that our estimator uses all the information. Often we find that if we're looking for the minimum variance unbiased estimator, we know that this MVUE is it's an unbiased estimator which is a function of a sufficient statistic. So we can often just try finding the MLE, the maximum likelihood estimator, because we know it's a function of a sufficient statistic. And then we can try to correct its bias. So try bias correcting the MLE. I can write that more neatly. So we can try to get the MLE, figure out its expected value, and then maybe correct the bias. And this can lead us to the minimum variance unbiased estimator. Okay, so MLEs are good in the sense that they use all the information contained in the data about the parameter. We're going to see this in an example. So let's jump right into it. We have x1 through xn, a random sample from the gamma distribution, where the value of beta is known to be 2, and so alpha is the only unknown parameter. Okay, so what we're going to do is try to figure out what the maximum likelihood estimator of alpha hat or of alpha is, and then we're going to kind of explore this idea or explore the fact that alpha hat should be a function of a sufficient statistic for alpha. But let's do part 1 first and just worry about getting the estimator. So to find the MLE, we need to write down the likelihood function. Which is going to be the product of gamma densities. So let me up here just write down the density, the PDF of this gamma distribution, just to have it on paper, not on paper, on the screen in front of me. Okay, alpha minus 1 e to the minus alpha over 2. This is for alpha greater than 0. Okay, so now what goes here is basically this thing, but I plug in xi. So I got 1 over gamma function of alpha, 2 raised to the power alpha, xi to the alpha minus 1, e to the minus xi over 2. And you know what? We do not always have to carry around these indicator functions. If the value of the parameter determines the support, then we do need to be very conscious of this indicator function. But I can just kind of keep in mind, okay, all my xi's have to be greater than 0, and then I can ignore this indicator function part. So we're going to ignore it. And let's simplify this a little bit before we go to the log likelihood, which will be the next step. Okay, so if I let this product operate on here, I'm going to get 1 over the gamma function of alpha. Let me keep it all together. So 1 over gamma function of alpha 2 raised to the alpha to the power n. Then letting the product operate on this part, I can write it as just product of xi raised to the alpha minus 1. And this, it's like I have alpha 1 to the power x minus 1 times x2 to the power alpha minus 1, and so on out to xn to the power alpha minus 1. So let me just write it as x1 times x2, everything raised to the power alpha minus 1. So it's product of the xi's raised to the alpha minus 1. Okay, I'm going to write it like that. So I'm going to take the product and then raise it to the power alpha minus 1. And when I take the product and let it operate on this part, it's going to come up as a sum. Okay, let's get rid of this clutter. Okay, so here is my likelihood function. This is supposed to be n. Here's my likelihood function. Now, what I should do is go to the log likelihood function, because what I'm going to want to do is take the derivative with respect to alpha of the log likelihood and then set that derivative equal to 0. I don't want to differentiate this function with respect to alpha because it involves all these products, and the product rule will give us a headache real fast. So we switch to the log so that products become sums. Okay. If I take the log of this thing, I get n log 1 over gamma function plus n log 1 over 2 to the alpha, and then log of this thing looks like alpha minus 1 log of this product minus sum xi's over 2. Let's simplify a little bit more. This part, I don't really like to have log of 1 over something, so let's write it as minus n log gamma of alpha, since this is like gamma alpha raised to the minus 1, and I can pull the exponent out of the log and put it in front. And then this here is like 2 to the minus alpha, so let me take minus alpha and put it out front. And I'm going to slide this way a little bit. and then I've got alpha minus 1, and this log of a product becomes a sum of logs. Sum log xi. And then I've got this other stuff also, I going from 1 to n over 2. There's my log likelihood function. The third step in finding the maximum likelihood estimator is to take the derivative with respect to alpha of the log likelihood and set it equal to 0. So whatever it is, we want to set it equal to 0 and solve for alpha. Okay, so let's do that. So the first difficulty is, okay, I've got to somehow take the derivative with respect to alpha of this. So it's going to look like minus n, and then I'll have in the denominator, because of the log, gamma of alpha, and then I'll need to do d by d alpha of gamma of alpha. Okay, by the chain rule. So that's what I get for the first one. Then for the second one, let's worry about this in a moment. We have not asked ourselves yet how we take the derivative of the gamma function. We'll worry about it in a second. So the derivative of the next part with respect to alpha is minus n log 2, and then we have plus sum log xi. Okay, and we're going to be setting this equal to 0. Let's take this and simplify it a little bit. Okay, so let's look at this part. Let's call the first derivative of the gamma function gamma prime alpha, so that this is like gamma prime alpha. Then this whole thing actually has a name. Let's denote this function by psi. This is the Greek letter psi of alpha. This is called the digamma function. Okay, so it's defined as d by d alpha of log gamma function of alpha. Okay, that's the digamma function. Digamma function. The software R has a function called digamma, so we don't have to worry about computing this thing. We're eventually going to go to R. Okay, so we can write the first derivative of the log likelihood function. Let me just come down here as minus n times this digamma function, whatever it is, minus, let's take this part and be a little bit clever. I can write n log 2 as the sum, I going from 1 to n, of log 2. And so then I can write this whole thing as the sum of log xi minus log 2. Okay, because I've got this negative sign here. And I can write all of that by using rules of logarithms as log xi over 2. Okay, so let me just put here the sum of log xi over 2, and I'm setting that equal to 0. Okay, and so alpha hat is the value of alpha which solves this. That should be a plus. Okay, coming from this plus. Okay, so that's interesting. I have no way on paper to get alpha out of this digamma function. That means we're going to have to go to the computer and create this function and then search for the value of alpha, which makes that function equal to 0. And that's going to be our maximum likelihood estimator. But what I want us to note about this is that alpha hat is determined by whatever value this thing takes. Is determined by sum log xi over 2. Okay. And this quantity is a function of a sufficient statistic. So earlier, in some earlier lecture, we showed that the sum of the xi's is sufficient, is a sufficient statistic for alpha. And this thing is a function of this. So it's basically log of the product of the xi's minus n log 2. Okay. And so whatever value this takes, it's going to determine the value of my a hat, because it determines which value of alpha sets this equation equal to 0. So we cannot write down what that function is. Like, I'm not able to tell you what the function is which takes the value, the product of the xi's, and turns it into the maximum likelihood estimator of alpha hat, but it does it through this equation here. So we're going to go to the computer and show how we can find alpha hat, and we'll also check out how it's related to this sufficient statistic, which is the product of the xi's. So we're going to start by just generating a data set from the gamma, a data set from the gamma distribution under some value of alpha. Let's say alpha is 3, and we'll generate a data set of size n. So our gamma n shape parameter is alpha, and the scale parameter is equal to 2. Beta is 2 in the problem. So that gives us our sample x. So there's our data. Now we want to compute the maximum likelihood estimator of alpha. Okay, and we realized on paper that we had no nice way of writing down the maximum likelihood estimator of alpha. So what we had to do was find the value of alpha for which some function was equal to 0, and that function was one that we're going to define. So I'll just call it the a function. It's a function of, we'll call it alpha function. We had alpha, it depended on alpha and x, and so this is a way of defining a function in R. We're going to compute some value and return the value based on input values of alpha and x. And so inside the function, I also need to get n, so it'll be length of x. So we're going to do minus n times the digamma function of alpha minus sum of log x over 2. This was our function. So the digamma function, if you want to read about it, is here. So digamma function, it tells us about what it is here. So it's this gamma prime over gamma. Right. So we want to do that, And then what we want to do is take this function and find the value of alpha where it's equal to 0. This was supposed to be a plus. Okay, so we've got to look back at our paper to know that that's a plus. So the function I'm working with, so unit root is an R function which finds roots of a function. So the function is going to be this alpha function. I got to tell it some interval. Let's have it look over 0.1 up to 5, or I don't know, 10. And I have to give the value of this other argument to the function, so x equals x. And I would just want to pull the root. So here's my maximum likelihood estimator of alpha based on the data. Okay, so I get 2.95. So that's great. The true value of alpha is 3, and I estimated it to be 2.9567. So that's kind of close. What was our method of moments estimator of alpha? We didn't write it down on the paper, but let's do some comparisons between like the method of moments estimator of alpha and the maximum likelihood estimator of alpha. So how can we get the method of moments estimator of alpha? So expected value of the gamma alpha 2 distribution is 2 times, it would be alpha times 2 because it's alpha times beta, so it's alpha times 2. And so the method of moments estimator sets the first moment equal to alpha over 2. Okay, because it sets the population mean equal to the sample mean. So the first moment of the population equal to the first moment, sorry, this is alpha times 2. The first population moment equal to the first sample moment. So then we solve for alpha. So alpha, the method of moments, alpha is going to be m1 over 2. Okay, if I solve this thing for alpha. So it'll be interesting to compare the MLE to the method of moments estimator. So m1 is the mean of x. So this m1 is the mean of x divided by 2. That's the method of moments estimator. So we get something that's not too far away from the maximum likelihood estimator. Method of moments was 2.89. MLE was 2.957. So that's pretty interesting, but it'd be more interesting if we ran a kind of simulation. So let's compute 1,000 simulated data sets in a for loop. So I'm going to get a random sample x, and then I'm going to get the MLE on that data set. I'm going to store it in position s of some vector, and then I'm going to get the maximum likelihood estimator and store that in position s of another vector. So alpha MOM, create the empty vector. And so now I have 1,000 values of each of them. Part of why I wanted to do this simulation was also to show us how the maximum likelihood estimator of alpha depends on the sufficient statistic. So our sufficient statistic was the product of the x's. Okay, so this product is, it can take x1 times x2 times x3 and so on. So let's do product of the x's, and I need to create an empty vector to store my sufficient statistic. So numeric s. So let me run through all that. And what I want to show is if I plot the MLEs against the sufficient statistics, I'm going to get something that looks like this, okay, which is kind of ugly. So this product of the x's can get extremely huge because it's just taking the product of a bunch of numbers. So this is like not a nice looking graph, but we can see that it kind of follows a function. We would get a nicer looking graph if I just plot against the log. Okay, now we get this. So we see that there's some kind of function going on here. If I know the value of the sufficient statistic, I get the value of the maximum likelihood estimator according to this function. What I can also add to this plot is the maximum likelihood estimators versus the value of the sufficient statistic. And maybe we'll give these ones a different color, like red. And we get this. So the maximum likelihood, the method of moments estimator is kind of related in some way to the sufficient statistic, but it's not entirely determined by the sufficient statistic. And that's because the method of moments estimator does not use all the information in the data, because the sufficient statistic contains all the information in the data about the parameter, but the method of moments estimator kind of goes its own way, and you come up with some different values. So I think this is kind of interesting to show that even though I cannot write down the function which relates the sufficient statistic to the MLE for alpha in a nice way, I can see a picture of that function by making this plot. The last thing I want to do with this simulation is compare the mean squared errors of these two estimators. So I have in this vector 1,000 realizations of the maximum likelihood estimator, and I can compute the mean squared distance of my MLE from its target, alpha. Remember, the true value of alpha is 3. So I can compute the mean squared error according to my simulation by doing this. So I get that number. And if I compare it to that of the method of moments estimator, I see the maximum likelihood estimator was on average closer to the target value than the method of moments estimator. So that's kind of an argument in favor of the maximum likelihood estimator. I don't know. I doubt either of these estimates. Well, is it unbiased? I think the method of moments estimator is not unbiased, or is unbiased. So actually, yeah, if I look at the expected value according to my simulation of the method of moments estimator, it's closer to the target than the maximum likelihood estimator. We could show on paper that the method of moments estimator is unbiased, but if we look at the whole picture, which is the bias squared plus the variance, that gives us the mean squared error. The maximum likelihood estimator has a smaller mean squared error, meaning it must have a lower variance. And it achieves that by using the sufficient statistic and getting all the information out of the data. Let's look for the maximum likelihood estimators of the beta distribution based on a random sample from it. So we want to estimate alpha and beta using the method of maximum likelihood. Our first step is to write down the likelihood function, which is nothing other than the joint probability density function of x1 through xn regarded as a function of the parameters. So this is going to be the product, since they're independent. It's the product of their marginal PDFs. So we put in here the beta PDF xi alpha minus 1, 1 minus xi beta minus 1. We could also put here these indicator functions telling us about the support, but we're going to ignore them and just keep in mind what the support is. Simplifying this, we get this whole business raised to the power n, and then applying the product to this guy, we can write that as the product of the xi's raised to the power alpha minus 1, because it's like x1 to the power alpha minus 1 times x2 to the power alpha minus 1, and so on out to xn raised to the power alpha minus 1. Okay. And then we get product of 1 minus the xi's all of that raised to the power beta minus 1. So there's our likelihood function. What we'd like to do now is go to the log likelihood function and then see if we can differentiate it with respect to alpha and beta in order to set the derivatives, the partial derivatives equal to 0 and solve for alpha and beta. So let's write down the log likelihood. Okay, so we've got to take the log of all this stuff. So first, if I take the log of this, the n will come down, and I'll have log of gamma function of alpha plus beta. And then, since these are in the denominator, I'm going to write, well, so I could write plus log of 1 over gamma of alpha plus log of 1 over gamma of beta. But I prefer to write minus log gamma function of alpha and minus log gamma function of beta. Okay, I'm going to make myself, let's go down to the second line. The log of this part is going to be alpha minus 1. And then we have log of this product, but we're getting more comfortable with logs of products now. I pass the log through the product, and the product becomes a sum, like that. And for the last term, we then get beta minus 1 times sum log 1 minus xi. Okay, good. Now, if we look at this log likelihood and try to take derivatives, like what we would want to do is, let me use copy paste. We would want to take the partial derivative with respect to a and the partial derivative with respect to, alpha, partial derivative also with respect to beta, and set those equal to 0. And provided I can take those derivatives, and provided there's a unique maximum to this, a unique maximizer, then the solutions to these equations would be the maximum likelihood estimators, or the values of alpha and beta which maximize the likelihood function. What we notice, though, is it's going to get kind of messy again, because we're going to have derivatives of the log of the gamma function, which is going to be the di-gamma function, which we cannot write down in a nice way. So we're going to wind up having to search numerically for our maximum likelihood estimators. So what we're actually going to do is not go any further with looking at derivatives. What we're going to do instead is we're going to use R to find the minimizer. Okay, which are the minimizers? The minimizers of the likelihood. Okay. What we're also going to do in R is we're going to find the MLEs on a specific data set that we looked at before, I think, when we were doing method of moments. And I also want to make some comparison between the maximum likelihood estimators and the method of moments estimators on this particular data set. Okay, we're going to read in some data that we looked at before when we computed the method of moments estimators for the beta distribution. The data in X, these data are all between 0 and 1. There are a bunch of p-values for testing, like 6,033 different hypotheses about different genes. Like each hypothesis is this gene significant? Is that gene significant for predicting some outcome? Okay, we want to fit the beta distribution to these data. Previously, so I'm going to paste this in from another window, the method of moments estimators we could compute quite easily. We got the first two moments, and then we used these equations, and we got alpha bar and beta bar. So that's stuff we went through before. And let's see, we had made some plots of like when we overlay the density. So let me make that again. So let's do 9 length equals 9. Let's just add to our plot. So we've got our histogram x. We put frequency equals false so I can overlay a density. I just want to overlay a density on here, which is like the method of moments, the beta distribution under the method of moments estimators for alpha and beta. And so I'm going to do d beta at the x sequence shape 1 equals alpha bar and shape 2 equals beta bar against x sequence. So let me make this again, this again, this again. Okay, here's our picture. This curve is the PDF of the beta distribution under the method of moments estimators for alpha and beta. Now we want to compute the maximum likelihood estimators, so MLEs. To do this, we don't have any nice formula for computing them. We can write down the log likelihood function, but minimizing it is not something we can do on paper, so we're going to have the computer do it for us. So what we're going to do is we're going to use an R function called optim, which is different from, so before we used a function called uniroot, and that was for finding the roots of a function. We're going to use optim in this case because I want to minimize over two values. So optim allows me to put in a function which has a vector valued argument, and we can find the minimum or the maximizer of the function. Actually, optim always tries to find the minimum of that vector valued function, the minimizer of the vector valued function. So what I'm going to do is define a function called the negative log likelihood. Why am I going to use the negative log likelihood? The optim function finds the minimizer of a function. Okay. We want to compute the maximum likelihood estimator, so we actually want to find the maximizer. So I want to maximize the log likelihood, but that's the same as minimizing the negative log likelihood. So I can just do -1 times the log likelihood and minimize that, and it's the same thing as maximizing the likelihood. So here I'm going to put a function, and what I'm going to do is I'm going to make it a function of some parameter theta, where theta is going to wind up being a vector, where the first entry is alpha and the second entry is beta. Then I'm going to feed it the data x. I'm going to get from x the sample size. I'm going to get alpha as the first entry of theta, beta as the second entry of theta. And then I'm going to compute the log likelihood, which from our formula that we had on paper was like n times log of gamma function alpha plus beta minus log gamma function of alpha minus log gamma function of beta plus alpha minus 1 times sum log x plus beta minus 1 times sum log 1 minus x. Okay, that's the log likelihood. And now the negative log likelihood is going to be minus the likelihood, and that's the value I want to return from this function. Okay, so I've defined this function called negative log likelihood. I can see if the function works by putting in, like, let's see, I'll just drop in some values for theta. So I'll say theta equals 1 and 2, and x is my data. And so my function just computes some value which represents all of this evaluated when I put in alpha equals 1, beta equals 2, and the data x. Okay, but what I want to do using the optim function, I can look at the documentation of the optim function by doing question mark optim. And what I have to put into this function is this argument par, which are initial values for the parameters to be optimized over. So when I'm doing this numerical search for the minimizer of the negative log likelihood, what I need to do, like a lot of these search algorithms require that I put in some initial guess, and then it's going to start from that initial guess, and then it's going to move around from that initial guess and kind of search for the maximum. So what's nice is that we've already computed our method of moments estimators. We could use those for the initial guess. So I'm going to put in a vector which has alpha bar and beta bar as the initial guess. So it's going to start there, and then it's going to look around for the maximizer of the negative log likelihood function. And then I need to put in the function that I want to maximize. That's the negative log likelihood. And I need to put in also additional arguments to this function. So I want for this argument x to use the data x. Okay, and let's see how it goes. So I get a bunch of output from this. And if you read more about the documentation, this set of output is like the actual maximum likelihood estimators. So I'm gonna, if I want to pull this from the function without getting all this other output, I can do $par, and now I get those two values. So I'm gonna store that in something called theta hat, and then my alpha MLE is going to be, why don't I call it theta MLE? That's a little more explicit. MLE 1 and beta MLE will be the second entry of that. So beta MLE. So let's look at what those values are. Alpha MLE, beta MLE. Okay, these are the values. Let's see if they're very different from the method of moments estimators. So so my estimators of alpha from the method of moments and the maximum likelihood method are pretty similar. Also, my beta estimates are pretty similar. Maybe to get a better idea of how similar or different they are, we should go to our plot and add to it the PDF of the beta distribution under the maximum likelihood estimators. Okay, so now I have two curves in this plot. The black one is the PDF under the method of moments estimators, and the red one is the PDF under the maximum likelihood estimators. So that's kind of interesting. We get similar values. One more comment is that this optim function works pretty well. I don't have to even have reasonable values. I could put in basically any values, and I will still get the same answer for the MLE. This is just where it starts. So I could put 1 and 1. 1 and 1, that means it starts at a uniform distribution, and then it changes it until it gets to the maximum likelihood estimate. So, but if you've already computed the method of moments estimators, you can drop those in as initial values, and maybe the algorithm which maximizes the function will run a little faster. Of course, this is fast no matter what we put in, but usually we try to make a wise choice of initial values when we're using this kind of algorithm. This example I'm not going to go through, but you can look on the course website for the R supplement to Lecture 11, and I go through this example in there. Okay, the last result we're going to learn about maximum likelihood estimators is that if we're interested in estimating some function, say tau theta of a parameter theta, using the maximum likelihood approach, this theorem says all we need to do is find the maximum likelihood estimator for theta and apply that same function tau to theta hat, and we get the maximum likelihood estimator for tau of theta. So the idea is if we were to reparameterize the problem in terms of tau theta and then go back and do the maximum likelihood procedure for finding an estimator, we would find the estimator to be just the MLE for theta with the function tau applied to it. So I'm not going to go through the proof. The proof is in the handwritten notes. I would rather just spend time going through some examples of this. Here's the first one. Let's say I've got some random variables which are independent normal, and they have mean zero and standard deviation sigma. Okay, so it's like we've got epsilon 1 through epsilon n are independent normal, and mu is 0, and well, I'll just put 0, and then the variance is sigma squared since the standard deviation is sigma. But in the first one, we're going to just find the maximum likelihood estimator of sigma, regarding sigma as the parameter, and then we're going to find the MLE of sigma squared, regarding sigma squared as the parameter, and we'll find that the maximum likelihood estimator of sigma squared is going to be like sigma hat squared. Okay, so we just apply the same function to our estimator. So let's do this first one. So we want to write down the likelihood function. Our parameter is sigma. Our data are these epsilons. So it's going to be the product of normal densities where mu is 0 and the standard deviation is sigma. So I've got mu is 0. Okay, so I've got a 0 in the position of mu. And to simplify this, when I make this product go on to these guys, I have 1 over root 2 pi raised to the n, 1 over sigma raised to the n. I should have this on like do not disturb or something. And then I've got, when I wrote down the likelihood, I should not have had a sum up here already. Okay, the sum up there is going to come when I take this product. Okay, so this is the likelihood function. After I take the product, then it comes up here and becomes a sum. So sorry about that. Okay, and then I've got epsilon minus 0 squared, so it's just epsilon squared. Okay, good, so there's my likelihood function. Let's get the log likelihood function so that I can then differentiate it with respect to sigma, set that derivative equal to 0, and solve for sigma, and thereby get the maximum likelihood estimator of sigma. So I get n log 1 over root 2 pi plus n log 1 over sigma minus sum of the squared epsilons over 2 sigma squared. For reasons that might not make sense to you now, I don't like the way this part is written. I'm gonna change it regarding this thing. so 1 over root 2 pi is like 2 pi to the minus 1/2. So I'm going to pull that minus 1/2 out and put minus n over 2 log 2 pi. I don't know, it just looks better to me. And then this thing I'm going to write as sigma to the minus 1, okay, and pull the minus 1 out. So I'm going to get this minus 2. Okay, there's my log likelihood. Now to find the MLE of sigma, I want to differentiate with respect to sigma this log likelihood and set equal to 0 whatever I get. So taking this derivative, I get nothing from the first one. Okay, the second one I get minus n over sigma. And here, differentiating with respect to sigma, I've got sigma to the minus 2, because sigma's down here, so I'm going to get this minus 2 will come out, changing this to a plus, and canceling with this 2. And so I'm going to have in the bottom sigma to the power 3. Okay. And I'm going to set that equal to 0. And now I want to solve for sigma. So if that is equal to 0, I can send this over to the other side. And then divide both sides by n. And then multiply both sides by sigma squared. Or multiply both sides by sigma cubed. So that I get this. And then I can take the square root of both sides and get the maximum likelihood estimator of sigma. Okay, so here is my MLE for sigma. Okay, so I take the sum of the squared epsilons, divide by n, and take the square root. So the square root of the mean of the squared epsilons. Okay, now let's say I directly want to estimate sigma squared, which I'm going to give the name of tau. I want to find the maximum likelihood estimator of that. So now what I'd like to do is write down the likelihood in terms of this tau, which is sigma squared, epsilon 1, epsilon n. Okay, so now whenever there was a sigma, I'm going to put root tau, and wherever there was a sigma squared, I would put tau. So I've got, this is the product, 1 over root 2 pi, and I would have written 1 over sigma, like here, but now I'm doing this in terms of my new parameters. So this is square root of tau, e raised to the minus epsilon I minus 0, 2, and then here we have our tau, which is sigma squared. And so this, if we simplify it, we get 2 pi. Okay, well I can do it 1 over root 2 pi to the power n, 1 over root tau to the power n, e raised to the negative sum of the squared epsilons over 2 tau. Okay, so that's the likelihood. Now I want to get the log likelihood. So I take the log of this, doing the same simplification as before to this. So I'm going to basically put n over 2 and get rid of the square root. And then I'm going to put negative n over 2 and move this up into the numerator. And now we can see that when I take the log of it, I get this. I'm going to do the same thing here. I'm going to put the root 2 here and get rid of the square root. And then I'm going to put negative n over 2 and then move tau into the numerator. So now I get minus n over 2 log tau. And then taking the log of the last bit, I get sum of the squared epsilons over 2 tau. Now I want to take the first derivative with respect to tau of my log likelihood function. Okay. This gives me nothing. This gives me minus n over 2 tau. This part, since I have tau in the denominator, it's like tau raised to the minus 1. And so I'm going to get a minus 1 coming out front, making it plus 2 tau squared. And I'm setting this equal to 0. Having set that equal to 0, I can move this onto the other side, getting sum of the squared epsilons over 2 tau squared equals n over 2 tau. I can multiply both sides by 2. I can divide both sides by n. And I can multiply both sides by tau squared. So then I get tau squared over tau, which becomes tau. So that's going to be my tau hat. Okay, so the maximum likelihood estimator of tau is this tau hat, which is the sum of the mean of the squared epsilons. Notice that my estimator of sigma using maximum likelihood was the square root of this thing. And so we see that tau hat is sigma squared hat, because tau was sigma squared. Okay. So it sort of like doesn't matter if I want to estimate a function of a parameter. If I find the maximum likelihood estimator of that function of a parameter, it's going to be the same as just applying that function to the maximum likelihood estimator of the original parameter. Let's look at one more example of that. Actually, we'll do a couple more examples of it. This one, we've got the exponential distribution. So random sample from the exponential distribution. We often are interested in estimating lambda, but we might instead want to estimate the parameter 1 over lambda, which we could write as eta, give it a new name, eta. So let's find the maximum likelihood estimator of eta. So according to this result back here, okay, according to this result, since eta is 1 over lambda, eta hat, the maximum likelihood estimator of eta should just be 1 over lambda hat, where this is MLE of lambda. Okay. So I think we've already found the maximum likelihood estimator of lambda before. So from before, lambda hat, so I could write MLE to remind us that this is the MLE. The MLE of lambda was x bar, so we went through work to show that before. So eta hat, let me make a prettier eta hat MLE is just going to be 1 over x bar. Okay. So I think we studied this estimator before, and it's actually a biased estimator of eta. We had, I think, a homework problem about this. So the maximum likelihood estimator is not guaranteed at all to be unbiased. The only thing that's guaranteed is that it's a function of a sufficient statistic, which works in its favor. But we have to remember that that it's not unbiased. How about something that looks pretty different? What if we have an exponential distribution and we want to estimate the median? Okay, we know this lambda is like the expected value. So it's like the mean of the exponential distribution. But let's say we want to estimate instead the median. Let's think about how we would use maximum likelihood to estimate the median. Well, we need to express the median as a function of lambda. So if we can express the median as a function of lambda, then we can just plug in lambda hat. And that will be like the maximum likelihood way of estimating the median. So the median, we have to think back to how we find the median of a distribution. So if x has the exponential lambda distribution, we want to find the value, let's call it m, such that this probability is 1/2. Okay, remember the exponential distribution looks like this, where this is 0, and we want to find the value such that 1/2 of the area is here, 1/2 of it is here. So this would be the median. So this would be like PDF of exponential lambda. Okay, so if we want to find an expression for the median, this is like the CDF of x at m should be equal to 1/2, okay, because this thing is just the CDF, and the CDF is 1 minus e to the minus m over lambda. Okay, so we know by now the CDF of the exponential distribution. If we don't know it, we know how to find it. Remember, this is like 0 up to m of 1 over lambda e to the minus t over lambda dt. And so now we can rearrange this thing to get m by itself. And so I've got 1 minus 1/2 equals e to the m over lambda log of 1/2. This is just 1/2. Log of 1/2 equals minus m over lambda. So negative lambda log 1/2 equals m. So m hat, the maximum likelihood estimator of m hat, is going to be, when I plug in the maximum likelihood estimator of lambda here in this expression. Okay, so this showed us how to write the median as a function of lambda. So here, just plug in the MLE. Plug in MLE. Okay. So this is the maximum likelihood estimator of the median of the exponential distribution. One final example of really simple situation. x1 through xn are independent Bernoulli random variables. We want to find the MLE of p and the MLE of p times 1 minus p. So if I find p hat MLE, if this is the MLE of p, then I'm going to estimate p times 1 minus p by just taking that same function of the maximum likelihood estimator. So we really just have to do number 1. Okay. So to find the MLE, I'm going to get the likelihood function of p which is going to be the product of what? Of the marginal probability mass functions of x1 through xn. So the Bernoulli PMF is p raised to the xi times 1 minus p to the 1 minus xi. And I could, if I wanted, keep track of the support. So this is for the xi's equal to either 0 or 1, but I'm going to suppress these indicator functions. Simplifying this, this product can go up as a sum here and as a sum here. So I get p raised to the sum of the xi's, 1 minus p raised to the sum of the 1 minus xi's. So sum of the 1 minus xi's, here I'm taking the sum of 1 n times. So let me write this as n minus the sum of the xi's. Let's do one more thing to kind of make this nicer. Remember how we get the sample mean as the sum of the xi's divided by n? Rearranging this, we can write the sum of the xi's as n times the sample mean. I think this is nicer sometimes rather than writing this sum of the xi's all the time to just write n times the sample mean. Okay, so let's write the likelihood in that way. And now let's find the log likelihood. Okay, so we just want to take the natural log of this. So we're going to get n x bar n times log p plus n minus n x bar n log 1 minus p. Okay, and now we get to think about finding p which maximizes this, which maximizes the log likelihood. Okay. One thing that's kind of interesting about this likelihood is that if we look at it closely, and if we think about the possible values that x bar can take, it's possible that some terms of this disappear under certain samples. So it's possible that I could get a sample where all the values are 0, in which case the mean of the x's would be 0. And it's also possible that I could get a sample full of 1s so that I get no 0s. So in that case, the mean would be 1. And the other cases would be like x bar is between 0 and 1. And let's look at how the likelihood would change. So for x bar between 0 and 1, I would have exactly what I wrote down. For x bar equals 0, this term would go away, and so I just get n minus n x bar, except this is 0 now too. So I get n times log 1 minus p. If x bar is equal to 1, then this goes away, and this becomes just n log p. Okay, so p hat is going to depend on which case we're in. So let's look at these cases first. So maybe we write it like this. If x bar is 0, we think about what is the value of p which maximizes this. Remember, we're going to look for p in the interval 0 to 1. Maybe we're used to having open brackets, but let's think about closed brackets for now. It'll be less confusing. So the probability p is some number between 0 and 1. Let's suppose for a second that it could be exactly 0 or it could be exactly 1. This log 1 minus p is a, if I were to plot log p, this would be an increasing function of p. Log 1 minus p would be a decreasing function of p. So this is a decreasing function of p, which means to maximize it, I'd want to put in the smallest value of p possible. So I would put in 0 to maximize it. Okay. In this case, this is an increasing function of p, so I'd want to put in the largest value of p in order to maximize it, so I'd get 1. Okay, so it's like if I get all zeros in my data set, the maximum likelihood estimator for p is 0. If I get all ones in my data set, the MLE is 1. What is it in this middle case? We've got to take this and find its maximum. Okay, so what we're going to do is take the derivative of this and set it equal to 0 in order to find p hat in this middle case where I don't have all zeros or all ones in the data set. So taking this derivative, I get nx bar over p plus n minus nx bar over 1 minus p times minus 1 because of the chain rule. Set it equal to 0. So I get nx bar over p equals n minus nx bar over 1 minus p, sending this stuff over to the other side. I can divide both sides by n. And I can rearrange it again to get x bar 1 minus x bar, p 1 minus p, which tells me that p is equal to x bar. Okay, so so p hat is going to be equal to x bar in this case. Okay, so here I've got x bar, okay, where x bar is between 0 and 1. So actually, in every case, it's just equal to x bar. Okay. So to summarize, p hat MLE is equal to x bar for the Bernoulli distribution. And then, now we're into the citations page. So 2, we were supposed to find the MLE of p 1 minus p. And so we would just do x bar 1 minus x bar, because we plugged the MLE right into that function. Well, I think it's finished. Now we just will hope that it doesn't leak.